Okay, welcome. Today we're going to talk about the rate of change of a function. So go ahead and take your notes out and we'll get going. Remember, you can pause the video to get caught back up or rewind the video to listen to certain sections you may have not gotten the first time. So get your notes out and we will begin. Okay, the standard we're looking at is F.IF.6, and that says calculate and interpret the average rate of change of a function presented symbolically or as a table over a specified interval. Estimate the rate of change from a graph. Okay, there's a lot going on in that standard. The part we're going to focus on today is, and this is our objective, students will calculate the rate of change of a function over a specified interval. So go ahead and put the objective in your notes, and we'll move on and talk about some vocabulary. So pause the video now if needed and get the objective down. Okay, vocabulary. Again, this needs to go in your notes, and remember you might have to pause the video to copy the definition down. So rate of change, what is it? Well, the rate of change is nothing more than a ratio, okay, it's a key word, a ratio that compares the amount of change in a dependent variable, so variable depends on something, to the amount of change in an independent variable. An independent variable could be anything, any value. So we have the ratio that compares the change of a dependent variable, it's dependent on the independent, to the amount of change in the independent variable. So you go ahead and copy that down, and we'll kind of break that down and discuss what it means, rate of change. Okay, hopefully if you have not finished copying the vocabulary down, pause the video and finish it. And if you did, let's move on to the example. Okay, we're going to start with a simple example from Algebra 1, and this is just a line. And I'm going to pick 2 points on the line. So the first point I'm going to pick, let's put them right about here. We'll give them the coordinates x sub 1, y sub 1. Okay, so that's some x and some y, and the sub 1's mean it's going to be different than our second point. We're going to put him up here. And our second point we'll call some x, so x sub 2 and y sub 2. And the sub 1, sub 2 simply means these are 2 different x's and these are 2 different y's. So 2 different points on the line. If I'm looking for the rate of change, the ratio that compares how they change, so it's a ratio, so we know we're going to have division over here. I'm going to draw a little line here, leave some space because we're going to write some stuff in here. How did they change? Well, let's talk about vertical change first. Okay, this y value, if I draw a line over, is this much higher than that second point, or the first point, I should say. Okay, so how did it change? Or how do we figure out this distance? The distance is simply found by subtracting the 2 y's. So we could say y sub 2 minus y sub 1. Okay, we're going to apply the same concept for the x's. Now the x's, see if I can get this in here. So I'm going to have to drag this down a little bit, give me some room to write. Ooh, move my point. That's okay, we'll put another point back. So we're going to do the same concept with the x's. Use a green line. How did the x's change? Well, if I draw a line down, I can say the x's changed this distance from here to here. So how do we find that distance? How do we find the same way we found the y's. We're just going to subtract the x's. So I'll subtract the second x, which is here, from the first x. And this is our formula for rate of change. And that might look a little familiar to you because this is simply just slope. Our slope formula is the rate of change. So y2 minus y1 divided by x2 minus x1. And symbolically, that's written as what we call delta, that's a triangle, so we're going to say delta y over delta x. You'll see these symbols a lot in higher math and in your science classes. So know what they mean. Delta means the change in. It means I'm going to subtract them. So the change in y over the change in x. And that's my ratio that compares the dependent variables. Y is dependent on whatever value of x I plug into the equation to the amount of change in the independent variables. And remember, we can choose any x we want when we plug into an equation. Okay, so rate of change is simply just slope. Okay, go ahead and pause the video if you need to copy the examples down or you're falling a little bit behind. And remember, we're going to stay caught up. Turn the video back on, ready to move on to the example. Okay, here's our example. And we're going to find the rate of change over an interval. So I picked a parabola, U-shaped, some of the stuff we've been studying. And I'm going to pick an interval. Let's just say I want the rate of change from this point to this point. Here's my interval. We'll call that 1, 2, 3, 4. 1, 2, 3, 4. So our interval is going to be from -4 and it ends at 0. All right, different than the linear equation, the slope was constant. If we go back and take a look, my slope's going to stay the same. No matter what 2 points I pick, it's always the same slope. Now, in a parabola, the slope is constantly changing. So we're looking for about whatever this point is to this point. Notice the slope is steep, 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 and then it's getting less and less and less and less. Okay, so we're going to get a general idea of what the slope looks like. It's not going to be completely accurate, but it'll be close for our purposes, and we'll talk a little more about that as we go along. So identifying these points, let's see, our x value down here is 0, and our y value is 1, 2, 3, so he's -3. So over the interval, our point at the right side of the interval is 0, -3. On our left side, we have 1, 2, 3, that's -4, and 1, 2, 3, +4. Okay, so we have our 2 points, and we're simply going to use our slope formula. So the concept is that we can take some line and estimate the slope from point to point. Now, if we look at our graph, or the line I just drawn, we're going to say, you know what, that's not quite accurate. We'll talk about ways to make it a little more accurate. Okay, so let's find the slope of the linear line, or the line connecting the 2 points. Okay, that is simply just a slope formula, so let's go back and use our slope formula on this. Okay, so the rate of change, or our slope, is equal to the change in y over the change in x, or I'm just going to simply subtract the y, so we'll call him y1 and y2. So we're going to go -3 minus 4, which simply equals -7. Okay, we've got our change in y. Let's do the change in x. So we'll call him x1, since that was y1, and x2, since that was y2, and which points you call x1, y1, and x2, y2 does not matter. It'll all work out the same. So we could reverse them. So we want 0 minus a -4. 0 minus a negative is a plus. So the slope of my line connecting these 2 points, and that line is called a secant line. So the secant line that connects my 2 points is -7/4. Okay, so simply finding the slope of a linear equation versus the slope over an interval of something that's not linear, where it's constantly changing, is done the same way. Change of y or change of x. Now, if we wanted a more accurate slope, how could we do that? Think about that for a second, because we can see this line is not very accurate. from here to here, we can see our graph is steep and then kind of levels off. Wonder if we did this. Think about this. Let's try to get a better slope. Let's get all this stuff out of the way. We don't need him anymore. Let's move our points. Now this is the slope over the interval -4, 0. Wonder if I took my slope over, let's just say this point right here. So let's move our interval to -4, -3. Now, we're going to kind of simply estimate the point because it's not quite going through -3, but we're going to say it's close enough just for our purposes to make the math easy. So again, our slope at this new interval is equal to, again, delta y over delta x, which is the change in y. So our new y, x and y, are going to be -3 and 0. And this will be our new x sub 2 and our new y sub 2. So we're going to subtract our y, so that's going to be 4 minus 0, 4 minus 0. And notice I switched the points around. Instead of doing y2 minus y1, I'm going to do y1 minus y2, because you can do that. It's going to be the same. Over -4 minus -3. So 4 minus 0 is 4. 4 minus -4 minus a -3 is the same as -4 plus 3, or -1. And our slope is going to be -4. Now let's connect those with a line. This time our line looks something like this, our secant line. And let's change the color so we can get a better view. Let's go yellow. No, not yellow. Let's go dark blue. That's a good one. Okay, that line is a little more accurate to the graph. It's a little bit closer, and we simply did that by moving the points closer. So we had our old line, our old secant line over the interval -4, 0. You can see how far it is away from the graph. We shrunk our interval, put the points closer together, and we can see the line more fits the graph. So I'm saying, if you're looking for the rate of change of the left side of the parabola, I'm thinking this might be a little more accurate, a -4 slope. Okay, so this is how we find the rate of change, and I'll leave you with this question. How can we get even a more accurate slope than -4? So I want you to think about that for what we've done, and if you have any questions, please raise your hand, and I will come around and help you. Okay, thanks for listening to my video, and you know, I'm a amateur at making videos, and I appreciate you bearing with me. Hopefully they're getting a little better. So I will talk to you in class.